In this video, we're discussing learning outcome number 2 in lesson 4.4, which is all about understanding and applying the factorial rule. So before we get started, I wanted to go over the learning outcomes for 4.4 again, so that we can put this factorial rule in context. Remember, in this chapter, in this lesson, we are learning 5 methods for counting. In the last video, we learned about the multiplication counting rule. In this video, we're going to learn the factorial rule, which is just a special case of the multiplication counting rule. Then in the next few videos, we're going to learn about permutations and combinations. We're going to learn about permutations with identical objects. We're going to learn about permutations with distinct objects, and we'll learn about combinations with distinct objects. Now, all of this is important because when we're talking about probability, it's important that we are able to accurately count the number of outcomes in a certain category. So if we're trying to count the number of outcomes associated with event A, we need to be able to do that. Or we might be interested in finding the number of outcomes in a sample space. These 5 rules will allow us to count those outcomes most of the time. Now, these 5 don't cover everything, but they cover most of what you'll need if you are looking at real-world applications of counting problems. So let's start with the definition of factorial. Factorial is denoted by this exclamation point. It doesn't mean you're excited. It actually means something mathematically. This denotes the product of decreasing whole numbers. So if I'm looking at 5 factorial, there's a number to the left of that exclamation point. It's 5. 5 factorial is this. You start with 5 and then you multiply all the way down, decreasing that integer by 1 every time until you get to 1. So 5 factorial is 5 times 4 times 3 times 2 times 1. 3 factorial, for example, is 3 times 2 times 1. Now, if n is a positive integer, we can also represent n factorial using this notation. So we start with n, and then we multiply by 1 less than n, that's n minus 1. And then we multiply by 1 less than that, that's n minus 2. And we keep going until we get to 3 times 2 times 1. And by definition, 0 factorial is equal to 1. It's based on something called the gamma function. If you decide to take calculus, you'll learn a little bit about the gamma function. It's actually covered in the calculus book, but not often covered in calculus classes. But that's what that 0 factorial is based on. And all of this is related to the factorial rule, which is discussed on the next slide. So here's the factorial rule. The number of different arrangements of n different items, when all n of them are selected, is n factorial. When you're talking about arrangements of something, what you're saying is that the order matters. So I think the easiest example that I could think of was like a dinner party. Let's say it's Thanksgiving and you've got 12 people coming over. You might ask yourself, how many different seating arrangements are there for these 12 people? We've got 12 seats. If there are no constraints, so couples don't need to sit together, parents don't need to sit with their children, if people can sit anywhere at this table, how many different possible ways can I arrange these 12 guests at my dinner table? Well, if I've got 12 people, I've actually got 12 options for that first seat. Now, once I fill that first seat, I've got 11 options for the next seat, 11 people that could sit in that next seat. And then next to that person, I've got 10 options. And the person next to that person, well, there are 9 possibilities left, and so on. And we go all the way down the list until we've got 2 seats left and we've got 2 people left. And then we put that second to last person in that second to last seat. And then you've only got 1 person left for the last seat. So you have 10 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 3 times 5 times 4 times 3 times 2 times 1, which is 12 factorial. Now, I don't expect you to actually multiply that out by hand. We've got calculators for that. It turns out that 12 factorial is 479,001,600 seating arrangements. So that's how many seating arrangements we would have if we have 12 guests and no constraints on who sits next to who or who sits across from who. So that is an example of the factorial rule in action. Here's another example. It's a classic, before I get to that other example, This is just me outlining what I just said. Um, this is based on the principle, the factorial rule is based on the principle that the first item may be selected n ways. So if you've got n of them, well, you've got n possibilities for that first item. And then if you've already taken one away, there are n minus 1 possibilities for the second item and n minus 2 possibilities for the third item. And then because of the multiplication rule, you just multiply all those together. Well, that's the definition of factorial. So this is really just a special case of the multiplication rule. Now let me get to that classic problem that I was mentioning. One classic problem in combinatorics or counting is the traveling salesman problem. I've got a little map up here in the top right-hand corner of the screen. It's got the continental United States on it, and it's got one path, one way that you could visit all 48 capitals and then end up back where you started. So let's say we start in Tallahassee, and then we go up the East Coast, and we go all the way around the country, and then we come back and we're back in Tallahassee. So that's one way that you could visit all 48 capitals in the continental United States. We've got our little traveling salesman here on the right as well. I guess I don't know if that's even appropriate anymore. I don't even know if there are traveling salesmen these days, but this is a classic problem in combinatorics. So let's say we've got a traveling salesman, and he has to personally visit 5 cities. The first question is, how many different travel itineraries are possible? So how many different ways could he visit all 5 of those cities? And then the second question is, if the itinerary is randomly selected, what is the probability that the cities will be visited in alphabetical order by name? Okay, so let's answer the first question first. You've got 5 different cities. The number of different itineraries is just 5 factorial, because you've got 5 options for the first city, 4 options for the next city, 3 options for the third city, 2 options for the fourth city, and then you don't have any options for the last one. You're just going to visit the last one. You multiply all of those together, and it turns out that there are 120 different travel itineraries if you want to visit 5 cities. Again, this is just the multiplication counting rule, as I just said. Okay, now let's look at the second part. It asked, what is the probability of visiting those cities in alphabetical order? Now, if we assume that all 5 cities have unique names, so we're not visiting Springfield in one state, and then visiting Springfield in another state, and then visiting Springfield in the next state, but all 5 cities have unique names, and there's only one way to list them in alphabetical order. So the probability of visiting those cities in alphabetical order is the number of ways that the cities may be visited in alphabetical order, which is 1, divided by the number of ways that the cities, all 5 cities, may be visited. So that's 1 out of 120, and that's our probability. So that is a classic example of the factorial rule, and I will see you in the next video to study learning outcome number 3.